Okay guys, this is our first video on our last unit on solution. So this may be our very before last or last video for the year. The objectives: we will be able to describe the energy changes that occur in the solution process in terms of the solute-solute, solvent-solvent, and solute-solvent attractive forces. Describe the role of disorder in the solution process. We will rationalize the solubility of substances in various solvents in terms of their molecular structures and intermolecular forces. We will also define mass percent, part per million, mole fraction, molality, and calculate the concentration in any of these concentration units. Your homework is quest solution basics. You will have 3 quests for this unit. So here's the first one: solution basics. Now, those are terms you already know. Let's just quickly review them. Those are important terms you need to go over. Before I do that, let me show you a few animations or videos, and then we will come back here. Let me go here. I need for you to look at this. This is a solution. You have a super saturated solution. If you remember for the alarm, what did not happen, if you have a seed of that substance, it will create more opportunity for those particles to really settle and solidify. So you have a super saturated that comes into that form a crystal. Alright, something else. Let me minimize this. I'm going to show you. Okay, we had this problem right here. Let me show you something here. I need for you to look at this carefully. You have a solvent. That solvent, let's say it is water. Water that has that is dipole. Water will be attracted. This is an ionic compound. You have your solute. Those solute you will separate. The water will attract the positive ion and the negative ion, and that's what happened in dissolving. Okay, to dissolve. That's what happened. Let me show you 2 more things before we go back. This is our ionic compound. This is, let's say this is salt. You dissolve it in water. That salt will not only dissolve, it will also ionize. It will dissociate. It will form ions in solution. And as you already know, because of those ions, it will conduct electricity. Okay, one more. Okay, this is our salt. If I put it at the micro for you to see the particles, right here, sodium chloride, you can clearly see that the ions will dissociate. But if I choose a molecular compound, let's say this is sugar, you will see the molecules, they do not dissociate. So you have molecules of sugar, you do not have ions. Therefore, that's why they do not conduct electricity. Okay, let's go back. Let's review those terms. Solutions, you learned last year, solution is a homogeneous mixture of 2 or more substances. Solution, homogeneous mixture. What is the solute? The solute is a substance that is present in smaller amount. Because remember, solution does not mean liquid. A solution can be solid, liquid, and gas. Air is a solution. It is a mixture of different gases. The doorknob or bronze, they are solution. They are solid solution. And we have sugar water is a solution. The amount that is in lesser amount, the substance that is in lesser amount is your solute, and the one that is in greater amount is the solvent. What is solubility? Is the amount of that substance that can be dissolved in a given quantity of solvent, often expressed in grams of solute per 100 grams of solvent. Gram solute per 100 grams solvent. Another term you learned last year is miscible. Some people will say mixable. It is miscible. Two liquids that dissolve in each other in all proportion. And the opposite of miscible is immiscible. Like oil and water are immiscible. But two liquids that can mix completely, they are miscible. And molar solubility is the number of moles that dissolve per liter of solution, which is really molarity. Molar solubility. Now, I took this straight from your flip chart from last year. Those are factors that affect solubility. Those factors are temperature. Remember, for solid in a liquid, as temperature increases, the solubility of a solid in a liquid will increase, even though you have few exceptions. Stirring also, agitation, it is another factor that will affect solubility. Another one is surface area of solute. As you increase the surface area, the solubility of that substance will increase. Those are two graphs for you to compare the solubility of solids in a liquid and solubility of a gas in a liquid. As you can see, as the temperature increases, the solubility of most ionic compounds will increase. Increase temperature, increase solubility. But for gases, it is the opposite. As you increase the temperature, the solubility of a gas in a liquid will decrease. And what exactly? That's what happened for thermal pollution. As the temperature increases during a hot summer, the solubility of oxygen in the lake will decrease. That's why some fishes will die in the lake. Thermal pollution. Okay, decide whether liquid hexane or liquid methanol is the more appropriate solvent for the substances grease and potassium iodide. Now, if you have the liquid hexane, if you draw the structural formula for hexane, you will see it is nonpolar. Because it is nonpolar, it's going to dissolve in a nonpolar solvent, which will be grease. Nonpolar will dissolve nonpolar. But if we have methanol, which is polar, okay, with hydrogen bonding, methanol polar, it will dissolve in potassium iodide, which is ionic. Ionic is polar, therefore potassium iodide will dissolve in methanol, and grease will dissolve in liquid hexane. Likes dissolve like. Polar dissolve polar. Non-polar dissolve non-polar. Another concept we learned last year is the solubility and pressure. This is Henry's law. As pressure increases, the solubility of a gas or in a liquid increases. Just think of a soda can. Okay, the company wants to dissolve the carbon dioxide in the soda, so they apply pressure. So as you increase the pressure in that can, the solubility of the gas in that liquid will increase. Okay, when you open it, then you decrease the pressure, the solubility will decrease, and your soda will become flat. Henry's law, the formula is pressure equal a constant time concentration. Pressure equal a constant time concentration or solubility. Or you can use your formula, solubility of gas 1 over pressure 1 equals solubility of gas 2 over pressure 2. So pressure and solubility, they are directly related. We also learned different qualitative ways to express solution. Okay, qualitative way to express concentration. We said the concentration can be unsaturated. That means it can dissolve more solute. If you add more solute, it will dissolve it. The solution can be saturated. That means you make it dissolve the maximum. It can dissolve at a specific temperature. So one question that always gets students confused: if you have a beaker, you have any container that has leftover solute on the bottom, it is not super saturated, it is saturated. When you see excess solute on the bottom, it is just saturated. So if you want it to be super saturated, you need to force it, you need to increase the temperature and force it to dissolve more than it can dissolve, and let it cool down slowly. It will become super saturated. That's when you put a seed of crystal in that container, it will produce more crystal. Super saturated. We also learned 4 different ways, or I would even say we learned last year 7 different ways to quantitatively express concentration. 7 ways. Okay, one of them is, so this is the most important part. So those you need to know. Molarity. And we learned that molarity is number of moles of solute per liter solution. And we use the symbol big M, capital L. And then the unit is mole. We learn about molarity, which is lowercase m. The formula is moles of solute per kilogram solvent, not solution. Kilogram solvent. We also learn percent by mass, which is mass of one component over the mass of all the components time 100. It is percent with the time 100. Percent by volume, same thing. It is a volume of part over volume of whole time 100. We learn ppm, percent by not percent, is part per million. The same formula. It is mass of one part over mass of the whole time 10 to the 6. And part per billion, ppb, is part over whole time 10 to the 9. We learn also mole fraction. Mole fraction is moles of one component over the total mole. You do not multiply by anything. And we said last year the mole fraction will always be between 0 and 1, and mole fraction is unitless. Now, if you would please pull out your calculator, let's do some examples. Okay, calculator please. Let's see. It says here a solution is prepared by mixing 1 grams of ethanol. 1 grams ethanol. Okay, even your periodic table, if you can have them ready, please. With 100 grams water. We have the mass ethanol, mass water, to give a final volume of 101 milliliter. They ask to calculate molarity. They ask for percent by mass. They ask for mole fraction, and they ask for molarity of ethanol in this solution. So let's practice all of them. So we have mass of ethanol, we have mass of water, we have the total mass. Let's start with molarity. How do we find molarity? Big M molarity equal moles. Let me call it ethanol. I will call it ET. Moles ethanol over liter solution. Okay, calculator ready please. Therefore, molarity equal, how do we find the moles of ethanol? It is the grams of ethanol, which is 1.00 grams, over the molar mass of ethanol, which is 46.0. Okay, thank you. 46.08 or 07 over the liter of solution, which is 101 milliliter, but remember it needs to be in liter. Therefore, it is 0.101 liter. Therefore, the molarity is 0.21 215. Thank you. Molarity is 215 molar ethanol. 215 molar ethanol. Okay, let's go with mass percent. Mass percent ethanol equal. Mass percent is mass of ethanol, which is 1 grams ethanol over the whole. So, okay, they already gave us the whole. No, they did not give us the total mass. Yes, it is 101. 101 grams total time 100. And the percent is 0.99. Thank you very much. It is 0.99% ethanol. Okay, they ask for mole fraction, and the symbol we use for mole fraction is a chi. It's a Greek letter, chi. Okay, pardon my Greek. Chi ethanol equal mole of ethanol that we already got from here. What is the moles of ethanol? 0.0217 0.0217 moles ethanol. Students usually forget. They forget to bring that moles down here. They forget it. Just put the moles of the other one and forget to repeat this here. 0.0217 plus the moles of the water, which is 100 grams divided by 18.02. 100 grams divided by 18.02. What is that moles? The total or just the moles of this one? No, this is mole fraction. It cannot be that. Yes. Okay. All right. Okay. Very good. The mole fraction is 0.00389 or 39 mole fraction. So your mole fraction should be between 0 and 1. And the last thing they ask for here is the molality. The molality equal the moles of the solute, which is, we said, is 0.20217 divided by the kilograms of the water, which is 0.1 kilograms. It is 100 grams, 0.1 kilograms water. The molality is, thank you, it is 0.217 molal, lowercase m, molal. So you see how we can practice all of them in one problem. Now here's another one. The electrolyte in automobile lead storage batteries is a 3.75 molar. Okay, this is our molarity. 3.75 molar sulfuric acid solution. Oh, this is a little bit different. That has a density of 1.230 grams per milliliter. They ask you for mass percent. This is very typical in free responses. This one. Mass percent molality. This is a little bit more challenging. They give you the density, they give you the molarity, and they ask you for mass percent molarity of sulfuric acid. My advice is always assume you have 1 liter solution. Always start by assuming you have 1 liter solution to make things easier. So if I have 1 liter solution, that's mean this is my density. 1 liter solution, I multiply my milliliter by 1000. So the grams of the solution is 1230. 1230 grams. This is solution. And then this is, they give me the molarity. If I assume 1 liter solution and this is the molarity, and I know molarity is moles per liter solution, that means the 3.75 Molar is really my moles of the solute. Okay, stay here with me. I'm analyzing as we go. That means it is my mole solute. Now, let's see if we can start solving. Calculate the mass percent. They asked me for mass percent. What is the mass of my solute? So if I have the mole solute, I can find mass solute. So I can multiply the moles by the molar mass of sulfuric acid to give me the mass. What is the molar mass of sulfuric acid? Okay, 98 point what? 02 grams sulfuric acid. So what is the moles times the molar mass? 367.58, and this is grams solute. So if I have the gram solute and I say this is my gram solution, the percent by mass is the grams of the solute, which is 367.58 grams H2SO4 over the mass of the solution, which is 1230 grams. This is solution times 100 equal. So what is the mass percent? 20. Okay, 360. Are you sure? Okay, 367.58 you said. That means 368 divided by 1230. It is 29.9. Okay, it is 29.9. 29.9% H2SO4. Okay, so this is calculate the mass percent. This is mass percent. How about the molality? The molality equal the moles of the solute. That's good. I label everything here. It is 3.75 moles solute, moles H2SO4 over the kilograms of the solvent. What is the kilograms of the kilograms of the solvent. Okay, all right, let's go. Do we have the liter of the solution, which is 1 liter? Do we have the volume of the solute? No, we don't have the mass of solution. Okay, molality, mole of the solute. Do we have the volume of the H2SO4? Give us the mass of the solvent. Okay, let's do that. You see, this is the mass of the solution minus the mass of the solute, which is 267.58 minus 367.58 grams of this H2SO4. Okay, can I have that answer, please? Cannot be. 862.42. Thank you. So this is our gram solvent. Gram solvent. Okay, this is a brilliant idea. Now I just put a kilogram. Okay, all right. So this is 0.867.42 kilograms of the solvent. So what is 3.75 divided by 0.867? 4.35. This is molal. Okay, 4.35. That was very good job, guys. Very good job. Now, what is the molarity again? 3.75. The molarity is 4.35. So you see, they are different. The other thing I need for you to remember, molarity, the big M, is temperature dependent, dependent temperature. Molarity is not temperature dependent. Common question for free responses. Molarity is temperature dependent. Molarity is not temperature dependent. Okay, let's see. I know the time is running. Let's see if I should stop right here. Alright, so I guess I have to stop because I already got a signal. Okay, let me go for 5 minutes. 5 more minutes. Let's go. Energy involved in solution formation. This is very important. We did not discuss last year. Listen carefully. There are 3 steps in the formation of a solution. Number 1, the solute particles need to expand. That means you need to break the intermolecular forces between the solute. And we learn in the thermal unit, which I am sure you remember very well, breaking bond is endothermic, is absorbing heat. So we have delta 1, delta H1, which is expanding the solute. It is endothermic. Okay, it is positive. We have a second step. The force of attraction, the intermolecular forces between the solvent also need to expand. Okay, so we are breaking, let's say that this is water, you are breaking the hydrogen bonds between the water molecules. So this is also endothermic. So you have delta H2, which is endothermic, it is positive. And you have delta H of the mixtures. Now you have there should be an interaction between the solute that you expanded and the solvent. There should be an interaction putting them together. This will be positive. I would call this delta H mixture. Okay, delta H3 will be negative because you are forming that a force between them, it is negative. So is the heat of a solution positive, negative, or what is it? Delta H solution, so it depends. If the force of attraction between the solute and the solvent that you are using energy to break is less than the force of attraction that will be formed between the solute and the solvent, if that force of attraction is greater, then the solution will be negative. The delta H of the solution will be negative. So it depends. Alright, so make sure you understand all 3 steps. Let's see if we can solve this. A certain soft drink is bottled so that I may not do that. This is Henry's law. I'm not going to solve it to save time because you pretty much won't have Henry's law in the AP. So I'm going to skip this. You just have to use the formula that we just saw. Concentration or solubility equal Henry's law's constant. It is a constant they will give you times the pressure. They are directly related. You just plug the numbers. Alright, next. What I need for you to see here, is this pretty much has to do with the vapor pressure we already discussed. We already discussed last time. If you have just water, okay, and you have a solution, those particles in the water, okay, pure water, will have tendency to escape easier and form a higher vapor pressure than the particles in the solution. We will discuss this more when we discuss colligative properties in part 2 of that video. Alright, and then this is a free response question. So those particles will escape more until you will have all the volume of that solution in one beaker, and the other one will end up being empty. Okay, the higher vapor pressure in the pure water than in the solution. We will come back to this next. Okay, I will stop right here. That's where we will stop for part B. And then we are exactly pretty much halfway. We will have only one more video and we will be done. So make sure you do your calm for the first unit, for the last unit, and enjoy your day. Bye.